Hello, in today's video, let's discuss about RC circuits. So let's first begin with the definition of a capacitor. So if you remember, a resistor is a circuit element that consists of two terminals, a voltage V that develops across the terminals, a current I that flows into the terminal, and we have the current proportional to the voltage. In other words, we have voltage given by I times R, where R is the resistance of the element. Similarly, a capacitor again is a two-terminal element. The difference being that the current is proportional to the first derivative of the voltage. Or I can write my IC as C times dV by dt, where C is the capacitance of the circuit element, right? So anytime we have an element where the current flowing is proportional to the first derivative of the voltage, we call that a capacitor. Now it so happens that if you integrate current over time, you get a charge. So for example, if I integrate the total current that is flowing into this capacitor, then I get a net charge which is equal to C times the voltage that is developed across the capacitor, right? And so this is the relationship or the capacitor. And so anytime we have two nodes in a circuit where you expect that there is some charge storage that can happen, then we model a capacitor between those two elements, right? Now the curious thing about the capacitor is that because I is equal to C dV upon dt, when dV by dt is 0, then current is equal to 0. So which means that when you have a DC voltage that is applied to a capacitor, then no current flows to the capacitor, or you can assume that the capacitor is open circuit for DC voltages. So now let's quickly revise this by doing a couple of examples. So determine the current flowing in the capacitor when V is equal to minus 20 volts. So in this case, the current is going to be 0 because this is a DC current, DC voltage. And so when there's a DC voltage applied, there's not going to be any current that's going to flow through the system. Now let's look at the second case, that is V is equal to 2 e power minus 5t volts. So here you see that the voltage is a function of time, right? And so we expect a current to flow and the current to be a function of time, and it's given by C dV by dt. Now let's look at this voltage a little bit closer. So we look at this voltage is a dying exponential. That is, it starts at 2 volts and reduces as time progresses, which means that we have here a capacitor whose voltage is reducing as a function of time, or in other words, it's losing charge or is discharging. Therefore, we expect that the current, if you now look at this capacitor, we expect that the current in this capacitor is actually going to flow out of the capacitor. So in our convention, we expect that the current that is going to be calculated, it is going to be a negative value, or in other words, the capacitor is discharging, right? And that's going to flow out directly from the derivative. So here, to find the current, I give C into d by dt of 2 e power minus 5t, which in other words, it's going to be minus 10c e power minus 5t amperes. So depending on the value of the capacitance, the current is going to be determined, right? So what you see here is that this minus sign is essentially giving you an idea that the current is actually flowing out of the positive terminal of the capacitor, indicating that this capacitor is getting discharged. Now, suppose I want to find the voltage at any time in the capacitor. The voltage is going to be related using the integral. So remember that dV by dt can be written as 1 by C into I of t. So the voltage can be determined by integrating the current over a given time period, and that gives us the voltage. Now, suppose the capacitor was initially charged to some voltage, then if a current flows, so for example, suppose here is a capacitor, and suppose this was charged to some initial voltage V0. Now, if a current flows into this capacitor, then we expect this V0 to increase. However, if we have a condition where the current is flowing out of this capacitor, then we will expect the V0 to reduce. Right? And that is essentially the charging and the discharging process. Now let's talk about the energy that is stored in the capacitor. So if I want to find the energy stored in the capacitor, I need to first start with the power. So for any circuit element, the power is always given as a product of the voltage and the current. So in this case, for a capacitor, this is going to be given by V of t into C dV by dt. Or in other words, the energy now stored in this capacitor is integral of this power over times t1 to t2, and that is basically given by integral of t1 to t2 C into V of t dV by dt times dt. Now assuming that the capacitance is independent of voltage. So when we look at very simple capacitors, we can assume this to be true, that this capacitance is independent of voltage. However, when we model devices, there are cases where the capacitance between two nodes will be actually a function of the voltage between them. Those kind of capacitors are known as varactors. But in this case, let's just assume that the capacitance is independent of voltage. So I can pull this out and write this as V of t dV, where the voltage varies from V1 to V2. So this is the energy stored, and so hence my energy can now be written as half C V2 squared minus V1 squared. Now this is the energy stored in the capacitor when the voltage changes from V1 to V2. Right? And what you see here is that it doesn't matter how the voltage changes, as long as the voltage changes from V1 to V2, the energy stored in the capacitor is going to be just half CV2 squared minus V1 squared. So initially, if you assume that the capacitor is discharged, if I assume V1 is equal to 0, then once I charge up the capacitor, the net energy stored in the capacitor is going to be given by half CV squared. So a couple of things to keep in mind about the capacitor is that, one, no current flows in the capacitor when the voltage is a constant. Number two, a finite energy can be stored in the capacitor, and this energy can be stored even when I is equal to 0. Right? Third thing is that an ideal capacitor does not dissipate energy, right? So in an ideal capacitor, once I store the energy, unless I intentionally discharge or charge them up, the energy is not going to be dissipated. And finally, what you see is I is given by C dV by dt. And in most practical cases, our current cannot be infinity, which means that it is impossible for the voltage across the capacitor to change abruptly. Means that dV by dt cannot be infinity, which means that the capacitor is inertial to voltage. Not abruptly change the voltage across the capacitor. The voltage across the capacitor will have to change gradually, and which means that therefore when you put a capacitor in a circuit, we expect the capacitor to slow down changes in voltages across the nodes it has been connected to. So now let's try and look at the charging process of the capacitor. So let's consider that I have a capacitor that was charged to some value of voltage V0, and I have a switch connected to a resistor here, and say I throw the switch at time t equal to 0. So initially, as we looked at in an ideal capacitor, this voltage is going to stay put in the capacitor because there's no room for the charge to move. Now when I provide a conductive path for the charge, then eventually this charge is going to move through the resistor and eventually discharge. Now what you see is that resistance is an impediment to current, right? In other words, it is going to be harder to move the charge if this R is higher. So I can say that the discharge time of the capacitor is going to increase if R increases. For example, if my R is 0, if it's a short circuit, then I will discharge the capacitor instantly. Otherwise, as my R increases, my discharge time increases. You also see that this time increases if my capacitance increases, because that means I have more charge and therefore it's going to take a longer time from the capacitor to discharge. So what you see here is that this time taken for the capacitor to discharge is going to be proportional to both the R and the C, right? And this essentially is the known as the time constant of the circuit. So now let's try and set up an equation and try to identify how does this circuit or how does this capacitor discharge its charge. So let's assume that at some time t, V of t is the voltage across the capacitor. So therefore, if there is a current in the capacitor, the current in the capacitor is given by C dV by dt, right? And this is a current which is flowing from the positive to the negative terminal of the capacitor. Now, because the capacitor and the resistor are connected in parallel, I also know that VR or the voltage across the resistor is also equal to V of t, which means that the current in the resistor is going to be given by V of t by R. Now, if I apply KCL at this point, I know that at all times IC plus IR should be equal to 0, and this implies C dV by dt plus V by R is equal to 0, or in other words, dV by dt plus 1 by RC into V is equal to 0. So this is the characteristic equation that drives the discharge of the capacitor. And so now this is a simple first order equation, so we can solve that. So I can collect the terms. I get dV upon V is equal to minus 1 by RC into dt. Right? So I want to find the expression for V of t. So let's first talk about it. So when t is equal to 0, my V of 0 was essentially V naught. And so I want to now find at some value of t, what is the value of V of t. So integrating both sides, so when I integrate the left side, I integrate from V naught to V of t, dV upon V should be equal to minus 1 by RC integral 0 to t of dt, which gives you V of t is equal to V naught e power minus t by RC. So what you see here is that the voltage, the discharge process of the capacitor, the voltage across the capacitor has an exponential decay. And so if I plot essentially V of t as a function of t, I start off at some point V0 and then I exponentially decrease all the way to 0. At time t equal to infinity should be 0. That is, at that time the capacitor is discharged completely. RC is a characteristic time and known as the time constant of the circuit. And suppose this time constant reduces, then my discharge is going to happen quickly. If this time constant increases, then I'm going to take a longer time to discharge. Right? So this entire process or this circuit can be described by this time constant, which is known as the RC time constant, and it's given by the product of R and C. And so you can see that within tau seconds, the voltage drops down from V0 to V0 into e power minus 1, or roughly 36% of V0. So within the first tau seconds, the voltage has already dropped to 36%. Now one key thing you want to remember here is that the rate of change of the voltage keeps reducing as you go longer in time. In other words, the charge is going to drop very quickly at the beginning, and then the rate of change of the charge drop is going to reduce. Right? So now let's look at an example. So it asks to find the time required for the voltage V0 in the capacitor to drop by 50%. Right? And here you have a circuit which consists of a 6 microfarad capacitor and a 2 kilo ohm resistor connected in parallel. So first thing is, you know that this is a discharge phenomenon. So we know that the voltage has to be written of the form V of t equal to some initial V naught e power minus t by RC. So always the first thing in such problems is to find the time constant of the circuit. So the time constant of the circuit is given by R times C, which is given by 6 microfarad times 2 kilo ohms, which is 6 into 10 power minus 6 into 2 into 10 power 3, or 12 milliseconds, right? So 12 milliseconds is the time constant. Now we know that the within one time constant the voltage drops to 36%. So now we want to find the time required for the voltage to drop to 50%. So I expect that time should be less than this time constant. So basically I want to find the time at which the voltage is V naught by 2, and let's call that time T half. So I can basically write T half to be essentially RC ln 2, which works out to 0.69 into RC, or roughly 8.32 milliseconds. So within the first 8.5 milliseconds or so, basically the voltage drops down to 50% of its initial value. Now let's look at the flip version. Let's try and see how do you charge up the capacitor. So now let's look at a case where I initially have a capacitor that is discharged, and say now I'm applying some voltage VA to this circuit, and I want to see how does the voltage or how does this capacitor charge up when I switch on the circuit. Right now again let's think about the process a little bit. What is the capacitor going to charge up to? The capacitor is going to keep charging up as long as there is a current flowing in the resistor. Now the current in the resistor is only going to stop when the capacitor charges up to the applied voltage, which is VA. So we know that VC at infinity should be VA, right? So that is the point at which the capacitor will eventually start charging up. And initially, let's assume initially that the capacitance is at 0 volts, right? Now let's talk about the impact of this resistance. So remember again, resistance is an impediment to current. It restricts the current that's flowing in the circuit, right? So if I have a larger resistor, it's going to take longer for me to charge. So if my resistance increases, my charging time is going to increase. Similarly, if my capacitance increases, again I need to dump in more charge, so my charging time is also going to increase. So again in this case, you see a similar phenomenon that the charging time is going to be proportional to both the R and the C of the circuit. Right? And again you see that this would be the time constant of the circuit which we care about. So now let's set up the equation that governs the charging up of this capacitor. Let's say at some time t, the voltage across the capacitor is Vc of t. If that is the voltage, then if I say the current in the current in the capacitor is given by C dVc by dt. Now this current, because the resistance and the capacitance are connected in series, this is the same current that's flowing through the resistor, and I know that the voltage across the resistor plus the voltage across the capacitor should be equal to the applied voltage by using KVL. So what I know is Vc plus VR should be VA, Vc plus VR is going to be IC times R is equal to VA, or you have RC dVc by dt plus Vc is equal to VA. And this is the characteristic equation that is governing this charging process. And so you see that this should have a particular solution. So the way we are going to solve this is we are going to find the generic solution and then find the particular solution for this equation, for the system. So to find the generic solution, for generic solution I'm going to set the constant to be 0. So the generic solution is given by RC dVc by dt plus Vc is equal to 0, right? And this is again similar to what we discussed in the discharging case. So the solution for this equation is going to have the form Vc is equal to A e power minus t by RC plus B. This is the generic form for the voltage in this system. Now let's put in the boundary conditions. So we need to get the values of A and B. So let's put in the boundary condition. So let's redraw the circuit again here. So I have an R and a C and the voltage that is applied. Right? So let's for now assume that at time t equal to 0, the voltage across the capacitor was some V of 0. And let's say that at time t equal to infinity, the voltage has to rise up to some V infinity. In our case, V of 0 is equal to 0, V of infinity is equal to VA. Right? So Vc of infinity is going to be equal to B, and that is equal to V of infinity. And Vc of 0 is going to be equal to A plus B, and that is equal to V of 0, implies A is equal to V of 0 minus V of infinity. And therefore, I can write the generic charge up condition as V of 0 minus V of infinity e power minus t by RC plus V of infinity, right? So what you see is that this is the eventual value that your voltage, your capacitor is trying to charge up to, and this is the gap between this value and what you're eventually getting there to. So if I now plot this as a function of time, you're going to look at a graph which looks something like this. Say this is your V of 0 and this is V of infinity. So what you see is that eventually your capacitor has to reach V of infinity. It starts off at V of 0 and it has a graph that looks something like this, right? And again you see here that it is dependent on this time constant tau. So for example, if I have a smaller time constant, the charge up is going to be quicker. If I have a longer time constant, the charge up is going to be slower, right? And so this again tells you what the impact of the RC time constant is going to be. And so in our special case, when V of 0 is equal to 0, V of infinity is equal to V of A, I can write my Vc of t as VA into 1 minus. So the voltage across the capacitor rises up exponentially, and it rises up with a time constant of RC. So these 1R 1C circuits are known as first order circuits because they're governed by a first order differential equation. And the key point is they are associated with one time constant tau, which is given by the RC product. So let's look at a couple of problems here. So in this circuit, find the value of V for t equal to 100 microseconds. So let's first identify what's happening in the circuit. So you have one capacitor here. So this is going to be a single time constant circuit. And now at time t equal to 0, you're basically closing the switch, and or in other words, you're powering this power supply, right? So hence what you see is you expect that this is a charge up case. That is, the capacitor voltage is going to start off with 0 and then eventually charge up to a final value. And how do you find out what is the final value that this capacitor is going to charge up to? So when the capacitor has finally charged up, you expect the capacitor to look like an open circuit. So to find V of infinity, let's redraw the circuit and assume that the voltage is, so what we do is to find the final voltage of the capacitor, we assume that the capacitor is open circuited. So in this case, what you see is that the voltage across these two nodes is going to be 12 volts because there is no current flowing here. So therefore we know that V infinity is going to be 12 and V of 0 is going to be 0 volts. So all that is left, therefore if I want to find the profile, so my voltage profile is going to look of the form 12 1 minus e power minus t by RC volts. So I need to find the RC time constant of this circuit. So how do I find the RC time constant? Now tau is equal to RC. This R is nothing but the R Thevenin that is connected across. So I need to essentially find what is the Thevenin resistance across the capacitor. And so that can be done very simply because I can consider the circuit to be so. When I do the Thevenin resistance, I short all voltage sources. So these are my two terminals of the capacitor. I have a 4 ohm resistor here and a 4 ohm resistor here. But this 4 ohm resistor is shorted because the 12 volt source is shorted. So this gives my R Thevenin to be 4 ohms. And so therefore my tau is given by RC, which is 4 into 8 micro, which is 32 microseconds. And therefore I have my voltage as a function of time given by 12 into 1 minus e power minus t by 32 microseconds. Right? And now let's think about what's going to happen. So we're asked to find what is the voltage at 100 microseconds. Now because the time constant here is 32 microseconds, we expect that within one time constant the capacitor charges up to 69% of its final value. So when you have 3 time constants, you expect the voltage to be pretty much close to the final value of the voltage, right? And so when you calculate the value, you'll find that the V of t is going to be very close to 12 volts, right? Which is what we expect. If you had given it another few more time constants, then essentially you would have treated the voltage across the capacitor to be 12, right? And so these are the kind of approximations we'd make later on when we do circuits, when we'll say that, okay, after a few 5 or 6 time constants, I'll assume the capacitor is fully charged. So here you're asked to find the expression for Vc of t and V0 of t for t greater than 0. So now let's first find out what is happening in the circuit. So at time t equal to 0, I'm switching off the switch. So in other words, that I'm removing the power supply from the network. So hence I expect that this circuit is a discharge circuit. In other words, my capacitor voltage should be of the form sum V of 0 e power minus t by RC. So the first step would be to first find what is V of 0 and then estimate the time constant of the circuit. To find out V of 0, I want to find what happens to this, what is the charge stored in the capacitor before the switch was turned off. Right? So to find that, let's look at the circuit prior to switching off the supply. So I had a 2 microfarad capacitor here, a 2 ohm resistor, a 4 ohm resistor, and a 12 volt battery. What happens on the other side of the circuit is not of our concern because this 12 volt is going to ensure all the voltages on the other side do not impact. So here I want to find the open circuit voltage across the 2 microfarad capacitor. So my Vc of 0 is essentially 2 divided by 4 plus 2 into 12 or 4 volts, right? So initially my capacitor was charged to 4 volts and eventually it has to discharge. So I have calculated V of 0. Now I need to calculate RC. And again here R is going to be the Thevenin resistance across the capacitor. So I need to find the Thevenin resistance of this entire network and then use that to calculate the time constant. So the Thevenin resistance of this network works out to 1.654 ohms, and therefore my time constant works out to 2 microfarad into 1.654, or it is nothing but 3.308 microseconds. And therefore I can write my Vc of t as 4 e power minus t by 3.308. Now remember, this is a linear circuit. What I mean by linear circuit is that all voltages and currents are going to have the same functional format as the capacitor voltage, right? So therefore V of 0 is also going to look of the form. So V0 is the voltage across the resistor, the 3 ohm resistor. So V of 0 is also going to be of the form sum V of 0 e power minus t by RC, where RC is the same RC here. So I can write this as V of 0 e power minus t by 3.308 microseconds, right? So as long as I find what that value of V of 0 is, then I have essentially solved the function also for the voltage across the 3 ohm resistor. So again, in circuits like this, it's essential to first find the time constant. All other circuit parameters essentially are going to behave similar to that, either a dying exponential or a rising exponential. So find the voltage across the capacitor at time t greater than 0 given Vc of 0 minus is 2 volts, right? So here again, remember the capacitor is an inertial element when it comes to voltage. Therefore, the voltage across the capacitor is not going to change across 0. So therefore we have a capacitor that is initially charged to 2 volts, and we want to basically now look at what happens to this voltage as time evolves. And since you have no other power supply in the circuit, we expect that this is again going to be a discharge circuit, right? And so therefore I can write the voltage across the capacitor as 2 e power minus t by RC. So again it boils down to finding the time constant of the circuit, and the time constant is nothing but the Thevenin resistance times the capacitance, right? So let's calculate the Thevenin resistance. So the Thevenin resistance may be calculated by finding what is the effective resistance seen by the capacitor. So let's look at its Thevenin equivalent circuit. And so basically let's assume I want to find out RTH. So I give an output voltage. I want to measure its current. This is 10, this is 20, and this is I1. So I can write I0 as 3I1. And then if I apply KVL in this outer loop, then essentially I have 10I1 plus 20I1 is equal to V0, or it's equal to 30I1. Therefore my Thevenin resistance is V0 by I0, which is 10 ohms. So that's my Thevenin resistance. So my time constant of my circuit is 10 times 1 microfarad, or 10 microseconds, right? And so therefore I can write my Vc of t hence as 2 e power minus t by 10 microseconds volts. So this is the voltage of the capacitor. So a couple of things to remember about first order systems. So first order systems can generally be reduced to a single resistor and capacitor. And they have, most important thing, they have a single time constant which is equal to RC, and that time constant is all that you need to know to identify all the possible voltages and currents in the circuit and their respective time evolutions. Right? Now what we'll also do later on is you'll see that we sometimes, even when we have complicated systems, we tend to approximate that system to a first order system just because it makes hand calculations easy. So we'll come back to these time constants many times. We'll come back to these single time constant circuits because they make hand calculations of circuits much easier.